In the YouTube video titled Lecture 3, Stream Ciphers, Random Numbers and the One-Time Pad by Christof Paar, Professor Paar commences by delineating the three major branches of cryptography, specifically emphasizing symmetric cryptography. He then elaborates on the nature and applications of stream ciphers, highlighting their utilization in modern technologies like cellular communication. Stream ciphers, Paar explains, operate by encrypting individual bits, contrasting them with block ciphers that process data in fixed-size blocks. He emphasizes the inherent simplicity of both encryption and decryption in stream ciphers, utilizing a visual representation to illustrate this concept. Paar proceeds to explore the relationship between stream ciphers and the shift cipher, emphasizing the modular operation that underpins both. The lecture then delves into the critical role of random numbers in robust cryptographic systems, introducing three fundamental types of random number generators: true random number generators, TRNGs, pseudo-random number generators, PRNGs, and cryptographically secure pseudo-random number generators, CPRNGs. Paar clarifies that TRNGs derive their randomness from physical processes and are considered truly unpredictable. He emphasizes their limitations, namely, their slow generation speeds and the inherent impossibility of recreating their outputs. This leads to a discussion on PRNGs, which generate random numbers deterministically and possess good statistical properties, but are deemed unsuitable for cryptographic applications due to their predictability. Paar then transitions to CPRNGs, which are designed to be computationally secure. He defines this concept as the infeasibility of predicting future outputs based on prior outputs using even extensive computational resources. This segment culminates in a detailed examination of the linear congruential generator, LCG, a prevalent PRNG susceptible to cryptanalytic attacks due to its reliance on linear equations with two unknowns. Finally, Professor Paar concludes the lecture with a comprehensive summary of the one-time pad, OTP, which is considered the gold standard in cryptographic security. He elaborates on its remarkable characteristic of being unconditionally secure, meaning its security is impervious to any computational attack, regardless of computational power. He concludes by highlighting the significant challenge of key distribution that necessitates secure transmission of the OTP key. From 0 minutes to 5 minutes of the video, Professor Paar sets the stage for the lecture by establishing the broader context of cryptography, emphasizing the three primary branches: symmetric, asymmetric, and protocol cryptography. He then introduces the two primary families of symmetric cryptography: stream ciphers and block ciphers, emphasizing that the lecture will focus on the former for the initial 2 weeks. The discussion then transitions to a real-world application of stream ciphers, the GSM cell phone standard. Paar explains the fundamental concept of voice encryption, where the voice signal is digitally transmitted and encrypted using a stream cipher, highlighting the use of a key bit, S, for this process. This stage of the lecture focuses on conveying the conceptual simplicity of the encryption process, which involves the addition of the key bit to the plain text bit to produce a cipher text bit. In the YouTube video titled Lecture 3, Stream Ciphers, Random Numbers and the One-Time Pad by Christof Paar, Professor Paar commences by providing a succinct overview of the classification of cryptographic algorithms. He reiterates the existence of three primary branches: symmetric, asymmetric, or public key, and protocol-based cryptography. The lecture's focus, however, is on symmetric cryptography, specifically its two subcategories: stream and block ciphers. Paar's initial exposition highlights the fundamental distinction between these two types of symmetric ciphers. He posits that stream ciphers operate on individual bits of data, whereas block ciphers manipulate blocks of data, typically 128 bits or 16 bytes in modern implementations. To illustrate the encryption and decryption mechanisms of stream ciphers, Paar presents a pragmatic example using the ubiquitous cell phone. This example underscores the essential role of stream ciphers in securing mobile communications. The heart of the stream cipher encryption process is characterized by modular 2 addition, an operation that involves adding the plaintext bit, SHI, to the key bit, C, and obtaining the result modulo 2. Decryption is achieved through the same operation, but this time, the key bit is subtracted. Paar then delves into the electrical engineering perspective, revealing the equivalence of this modular 2 addition to the XOR operation commonly utilized in digital gate design. A crucial question arises from this simplified encryption framework. How is the key stream generated? This prompts the transition to the second segment of the lecture, which focuses on the generation of random numbers and their significance in cryptography. Paar elucidates the existence of three primary types of random number generators: true random number generators, TRNGs, pseudo-random number generators, PRNGs, and cryptographically secure pseudo-random number generators, CPRNGs. TRNGs are characterized by their dependence on physical phenomena, such as coin flipping or roulette wheel rotations, while PRNGs rely on deterministic computations. CPRNGs, a subset of PRNGs, are specifically designed for cryptographic purposes and are distinguished by their unpredictable nature, a critical attribute for robust cryptography. Paar's explanation of the concept of unpredictability is paramount. He underscores the crucial role of CPRNGs in cryptography, particularly for the creation of secure and unique private keys. The lecture concludes with a discussion of the one-time pad, OTP, cipher, widely considered to be the most secure encryption method. However, its practicality is limited by the requirement for a keystream as long as the message and the inability to reuse the keystream. Paar emphasizes that the real challenge lies in the secure generation of the keystream, a critical aspect that will be explored in greater depth in the following week's lecture. From 10 minutes to 15 minutes of the video, Professor Paar delves into the pivotal role of modular arithmetic, particularly modulo 2 addition, within the realm of cryptography. To illuminate this concept, he employs the illustrative example of a straightforward stream cipher, where encryption entails adding a key bit to a plaintext bit modulo 2. The professor subsequently elucidates the equivalence of modulo 2 addition to the XOR operation, a fundamental logic gate in the realm of digital electronics. He underscores the significance of the XOR operation, which can be interpreted as a bit flip. XORing a bit with 0 maintains its original value, while XORing it with 1 inverts it. The professor emphasizes that this bit flip characteristic is crucial for the robust security of stream ciphers. Expanding on this theme, he delves into the diverse types of random number generators, RNGs, prevalent in cryptography, distinguishing between the fundamental categories of true random number generators, TRNGs, and pseudo-random number generators, PRNGs. TRNGs, as their name suggests, rely on physical processes, such as coin flipping or the inherent randomness of radioactive decay, to generate genuinely unpredictable sequences of random numbers. However, the professor aptly points out that TRNGs often present practical limitations due to their relatively slow operational speeds and inherent inability to be reproduced deterministically. In contrast, PRNGs are algorithmic constructs that generate sequences of numbers exhibiting apparent randomness, yet are in reality deterministic. Professor Paar introduces a widely used PRNG known as the linear congruential generator, LCG, which operates iteratively through the application of a seed value, a multiplier, A, an additive constant, B, and a modulo value, M. He demonstrates that LCGs can exhibit vulnerabilities to cryptanalytic attacks, as an adversary can effectively reconstruct the LCG after observing a mere 3 outputs, S1, S2, S3, enabling the prediction of subsequent outputs. Professor Paar further provides a straightforward mathematical method for deriving the values of A and B based on the observed outputs. From 15 minutes to 20 minutes of the video, the speaker delves into the fundamental concept of modular 2 arithmetic within the context of modern cryptography, emphasizing its profound significance in the realm of stream ciphers. He articulates the intrinsic link between modular 2 addition and XOR operations, elucidating the principle through a comprehensive tabulation of all potential combinations of adding 2 bits, X and S, modulo 2. This demonstration vividly illustrates the operational essence of an XOR gate. For instance, he emphasizes that 0 plus 1 mod 2 results in 1, while 1 plus 1 mod 2 yields 0. The speaker then proceeds to explicate the notion of true randomness and its paramount role in the generation of unique private keys. He employs the relatable example of coin flipping to exemplify this type of randomness, where each flip produces a truly random bit, underscoring the fundamental unpredictability inherent in such processes. From 20 minutes to 25 minutes of the video, Professor Paar delves deeper into the significance of modular 2 addition in the context of modern cryptography. He emphasizes the concept's paramount importance, despite its apparent simplicity. Paar then illustrates the application of stream ciphers through a straightforward example, encrypting the letter A. He assumes a key stream of 0100100 and performs a modular 2 addition on each bit of the ASCII representation of A, 65, or 0100001, resulting in 00011001, which corresponds to the lowercase l. Paar highlights the imperative nature of employing truly random bits, asserting that an adversary capable of predicting the next bit in the keystream could potentially decrypt the entire message. This underscores the paramount role of genuine randomness in cryptography. From 25 minutes to 30 minutes of the video, Professor Paar delves into the concept of XOR gates and their relevance in cryptography. He elucidates that an XOR gate executes a modular 2 addition, effectively inverting a bit if the key bit is 1 and preserving it if the key bit is 0. This leads to the critical realization that a 0 XOR'd with any bit remains unchanged, whereas a 1 XOR'd with any bit flips it. To exemplify this, he utilizes an instance of encrypting the letter A, represented by the binary code 01000001, with a key stream 01100011. The XOR operation is conducted bit by bit, yielding the ciphertext 00100010, which represents the lowercase letter l. This illustrative case underscores the pivotal principle. If you XOR a bit twice with the same value, you retrieve the original bit. From 30 minutes to 35 minutes of the video, Professor Paar transitions to a discussion of the one-time pad, emphasizing its notable security despite an initially unconventional name. He highlights that while frequently employed in military contexts, its practical implementation in commercial products is hindered by inherent complexity. Professor Paar underscores that reusing keys, even in seemingly discrete scenarios involving individuals like spies, constitutes a severe security vulnerability. He asserts that the one-time pad, characterized by its simplicity, achieves perfect security. This attribute stems from the cryptographic impossibility of replicating the key, which is generated using a true random number generator. To elucidate this principle, Professor Paar provides a demonstration using the letter A within the ASCII character set. Its binary representation, 01000001, 7 bits, illustrates that even with the most potent computational resources at their disposal, an attacker would be unable to decrypt the ciphertext generated by a one-time pad encryption. Professor Paar further concretizes this concept with a practical example of one-time pad encryption. He encrypts the letter A, 01000001, by adding a keystream of 01001011, resulting in a ciphertext of 00001010. This scenario exemplifies the fundamental principle of one-time pad encryption, where an attacker is effectively thwarted by the irreproducibility of the key, a truly random sequence of bits. From 35 minutes to 40 minutes of the video, Professor Paar elucidates the crucial role of random numbers in cryptographic applications. He distinguishes between 2 distinct categories of random number generators: true random number generators, TRNGs, and pseudo-random number generators, PRNGs. TRNGs, exemplified by the act of flipping a €2 coin, are characterized by their inherent randomness, albeit at the expense of computational efficiency. He then introduces the concept of a PRNG, emphasizing its deterministic nature and the possibility of its replication by an individual possessing knowledge of the underlying algorithm. The professor illustrates this concept with a rudimentary PRNG function where the initial random value, denoted as S0, acts as a seed. Subsequent values, S1, S2, S3, and so on, are calculated recursively using the formula C plus 1 equals A asterisk C plus B mod M, where A and B represent constants and M signifies the modulus value. Professor Paar further clarifies that the bit length of a PRNG, in this context, is determined by computing the binary logarithm of M and rounding the result upward. As an example, if m is set to 30, its bit length becomes log 2 30 equals 4.91. Rounding this value upward yields 5 bits. He then elaborates on the linear congruential generator, LCG, a commonly employed PRNG. Professor Paar reminds the audience of a previous example of an LCG encountered in the video, the rand function within the C programming language. The LCG is presented as a specific instantiation of a PRNG, particularly relevant in cryptographic applications. The professor proceeds to demonstrate how an LCG can be compromised through an attack scenario. He postulates that an attacker possesses knowledge of 3 plaintexts, x1, x2, and x3, along with their corresponding ciphertexts, y1, y2, and y3. Exploiting a system of equations, the attacker can subsequently deduce the values of A and B. Professor Paar concludes the segment by highlighting the inherent cryptographic vulnerability of the LCG. Given just 3 outputs, the attacker can effectively break the system and predict future outputs. He strongly advises against the use of LCGs in cryptographic settings due to their inherent weakness. From 40 minutes to 45 minutes of the video, the speaker delves into the paramount significance of stochasticity in the realm of cryptography, emphasizing its crucial role in the generation of keystreams. While acknowledging the inherent superiority of genuine random numbers, the speaker highlights their practical limitations, often necessitating reliance on physical processes such as coin tosses. As a viable alternative, the speaker introduces pseudo-random number generators, PRNGs, deterministic algorithms capable of producing sequences of seemingly random numbers. The speaker emphasizes that the linear congruential generator, LCG, a ubiquitous type of PRNG in real-world implementations, relies on an iterative update function. This function calculates the subsequent number in the sequence as a determined function of the preceding value, a seed value, and a modulus. Illustrating this concept with the rand function in the C programming language, the speaker provides the equation 1103515245 *s I plus 12,345 mod 2 to the power of 31, where s I signifies the preceding value in the sequence. From 45 minutes to 50 minutes of the video, Professor Paar delves into the critical role of randomness in cryptography, introducing the concept of pseudo-random number generators, PRNGs. He emphasizes that while PRNGs do not produce truly random sequences, their utility in cryptography hinges on a crucial attribute, unpredictability. Professor Paar elucidates that a PRNG is deemed cryptographically secure if, given a sequence of outputs, it becomes computationally intractable for an adversary to predict the subsequent output. To illustrate this concept, he presents a widely employed PRNG, the linear congruential generator, LCG. He demonstrates how an attacker can compromise an LCG by observing a limited number of outputs and exploiting the LCG's formula to calculate ensuing outputs. Professor Paar underscores that in this instance, observing only 3 outputs of the LCG suffices to completely undermine the generator. Specifically, the attacker can determine the parameters A, multiplier, and B, increment of the LCG using the following equations. A equals S2, S3, asterisk, S1, S2, caret dash 1 mod M, and B equals S2, S1 asterisk, S1, S2, caret dash 1 mod M. Here S1, S2, and S3 denote 3 observed outputs, and M represents the modulus of the LCG. From 50 minutes to 55 minutes of the video, Professor Paar embarks on an exposition of pseudo-random number generators, PRNGs, emphasizing their deterministic nature. While not truly random, these generators employ an algorithm to produce a seemingly unpredictable sequence. Professor Paar provides a concrete example, illustrating the linear congruential generator, LCG, through the formula S, I plus 1, equals, A asterisk S, I, plus B, mod M, where S, I, represents the preceding random number, A and B are constants, and M denotes the modulus. He underscores the importance of meticulous selection of these constants to ensure a statistically sound and robust sequence of random numbers. A salient vulnerability of PRNGs is highlighted. An adversary can effectively compromise the generator by observing just 3 outputs, thereby undermining its cryptographic utility. From 55 minutes to 60 minutes of the video, Professor Paar introduces the third category of random number generators, cryptographically secure pseudo-random number generators, CPRNGs. He emphasizes that while these generators are deterministically computed, their inherent unpredictability renders them impervious to cryptanalysis, even with access to vast computational resources. To elucidate this concept, he presents a common CPRNG, the linear congruential generator, LCG, and demonstrates how it succumbs to cryptanalytic attack by leveraging the solution of a system of linear equations. Specifically, the attack exploits the knowledge of 3 outputs, S1, S2, and S3, from the LCG to determine the key values, A and B, by solving the equations S2 equals A asterisk S1 plus B mod M and S3 equals A asterisk S2 plus B mod M. Paar emphasizes that the equations are classified as linear due to the absence of higher-order powers of the variables A and B, thereby enabling their solution using conventional linear algebra methods like Gaussian elimination. He concludes that while LCGs can generate sequences with statistically desirable properties when parameters are carefully selected, their susceptibility to attacks when an adversary can observe multiple outputs underscores the importance of employing cryptographically secure CPRNGs in sensitive applications. This reinforces the notion that even seemingly secure CPRNGs can be compromised with simple attacks. From 60 minutes to 65 minutes of the video, Professor Paar delves into the third and final classification of random number generators, the cryptographically secure pseudo-random number generator, CPRNG. This type of generator, unlike its predecessors, is characterized by the crucial property of unpredictability. This means that it is computationally infeasible to extrapolate future bits from a given set of preceding bits. The speaker expounds upon the definition of a CPRNG, emphasizing its computational intractability in predicting the subsequent bit based on any number of prior bits. As an illustrative example, Professor Paar introduces the widely employed CPRNG, the linear congruential generator, LCG. The LCG's functionality rests upon a straightforward recursive equation, where each subsequent output bit is determined by a function of its predecessor. A compelling demonstration follows, revealing how an attacker can exploit the LCG's vulnerability by observing 3 consecutive output bits and subsequently deriving the values of the constants A and B. The speaker concludes by underscoring the paramount importance of eschewing LCGs within the domain of cryptography owing to their inherent susceptibility to cryptanalysis. From 65 minutes to 70 minutes of the video, the speaker delves into the realm of pseudo-random number generators, emphasizing the significance of cryptographically secure pseudo-random number generators, CPRNGs, in the context of cryptography. The speaker underscores the deterministic nature of CPRNGs, whereby their output can be mathematically reproduced, and posits that their security is predicated on their unpredictability. To elucidate this concept, the speaker introduces a widely used CPRNG example, the linear congruential generator, LCG. The speaker expounds upon the underlying principle of the LCG, which involves generating a sequence of pseudo-random numbers via a straightforward recursive formula. A central point of emphasis is the vulnerability of the LCG, wherein an attacker can exploit the formula to effectively deduce the keystream. The speaker illustrates this vulnerability through a concrete example, demonstrating that an attacker can breach the LCG by acquiring 3 known outputs, S1, S2, and S3, and subsequently utilizing a system of 2 linear equations to solve for the key, comprised of 2 variables, A and B. The speaker meticulously outlines the solution process, demonstrating the susceptibility of the LCG to attack. From 70 minutes to 75 minutes of the video, Dr. Paar embarks on an in-depth exploration of pseudo-random number generators, PRNGs, emphasizing their indispensable role in the realm of cryptography. He underscores the paramount importance of unpredictability in PRNGs, clearly differentiating them from their counterparts, truly random number generators, TRNGs. which rely on the inherent randomness of physical processes. Dr. Paar then introduces the notion of a cryptographically secure PRNG, elaborating that these generators are meticulously crafted to render their output computationally intractable to predict. He then delves into the widely utilized linear congruential generator, LCG, a PRNG, providing a detailed and accessible explanation of its operational mechanism. Subsequently, Dr. Paar meticulously demonstrates a practical attack on the LCG, unveiling how an adversary can compromise the system by effectively solving for the key values A and B using a mere 3 outputs from the generator. He poignantly emphasizes that if an attacker gains access to 3 outputs from an LCG, they can confidently compute the entire generator and predict all future outputs with certainty. Dr. Paar concludes the segment by forcefully advocating against the use of LCGs in cryptographic applications due to their inherent vulnerability to such attacks, thereby highlighting the critical need for PRNGs that exhibit robust cryptographic security. In the YouTube video titled Lecture 3, Stream Ciphers, Random Numbers and the One-Time Pad by Christof Paar, Professor Paar delves into the crucial concept of unpredictable random number generation within the realm of cryptography. He underscores the paramount importance of true randomness, particularly for the generation of unique private keys, but he simultaneously acknowledges the inherent impracticality of such truly random sequences due to their irreplicable nature. As a pragmatic alternative, he introduces pseudo-random number generators, PRNGs, which employ deterministic computation. Professor Paar meticulously categorizes PRNGs into 2 primary types, Type A and Type B. Type A encompasses true random number generators, TRNGs, which are derived from physical processes. He illustrates this with the widely familiar example of coin flipping, where the outcome is truly random and cannot be replicated. In contrast, Type B pseudo-random number generators are deterministically computed, often using formulas and algorithms. Professor Paar introduces one such PRNG, the linear congruential generator, LCG, which calculates each subsequent value based on a seed value and a recursive update function. He emphasizes the simplicity and ubiquity of the LCG, particularly in software testing applications. However, Professor Paar emphatically cautions against the use of LCGs in cryptographic settings due to their inherent vulnerability to cryptanalysis. He demonstrates a practical attack that leverages known plaintexts and their corresponding ciphertexts. By reversing the XOR operation, the attacker can compute the keystream bits and subsequently deduce the key values used to generate the random numbers. This vulnerability is demonstrably simple, as exemplified by the formula A equals S2, S3, asterisk, S1, S2, ℏ-1 mod m, which can be used to compute one of the key values, A, from just 3 known keystream bits. Professor Paar's discussion extends to the profound implications of unpredictability in cryptographic security. He asserts that the predictability of a PRNG, even if computationally feasible, compromises its security. He emphasizes that a cryptographically secure PRNG must possess unpredictability, meaning that even with access to a substantial portion of the generated sequence, predicting the next value remains computationally infeasible. This notion is further emphasized through a scenario where the attacker can easily anticipate the next keystream value despite knowing the first 1,000 bits. This serves as a stark reminder of the inherent weaknesses of rudimentary PRNGs in cryptographic applications. Professor Paar underscores the critical role of key distribution, necessitating stringent measures to ensure the non-reuse of keystream bits in encryption. He cautions that an attacker gaining access to these keystream bits, whether through theft or illicit acquisition, can potentially decrypt the corresponding message, rendering the entire encryption system ineffective. Professor Paar's discourse on unpredictable random number generation is of paramount importance for comprehending the foundations of secure cryptographic systems. He advocates for the implementation of cryptographically secure PRNGs, emphasizing the paramount importance of unpredictability in cryptographic applications. This lecture provides a foundational understanding of the complexities and inherent vulnerabilities within the diverse spectrum of cryptographic techniques. From 80 minutes to 85 minutes of the video, Professor Paar delves deeper into the one-time pad, also known as OTP, which he reiterates as a stream cipher where the keystream bits are sourced from a true random number generator. This crucial characteristic ensures that each keystream bit is utilized only once, resulting in an exceptionally robust statement regarding the cipher's security. Professor Paar then transitions to the concept of a pseudo-random number generator, PRNG, frequently abbreviated as PRNG, elucidating that while it is deterministically calculated, it possesses the potential to generate sequences that exhibit the characteristics of true random numbers. He underscores that a cryptographically secure PRNG is a PRNG possessing an additional property, unpredictability, which is an indispensable component of cryptographic security. In conclusion, he emphasizes the significance of distinguishing between true random numbers, which are inherently unpredictable and cannot be reproduced, and pseudo-random numbers, which are deterministic and can be recreated. From 85 minutes to 89 minutes of the video, Professor Christof Paar delves into the realm of pseudo-random number generators, PRNGs, focusing specifically on the ubiquitous linear congruential generator, LCG. He elucidates the LCG's operational principle, which entails the iterative generation of a sequence of pseudo-random numbers through the application of a straightforward mathematical formula, SI I plus 1 equals A asterisk SI I plus B mod M. Within this formula, SI I represents the preceding pseudo-random number, A and B denote constants, and M signifies the modulus. To demonstrate the inherent vulnerability of LCGs to cryptanalytic attacks, Professor Paar presents a practical demonstration. This attack hinges upon the observation of 3 consecutive outputs from the LCG. These outputs are then used to construct a system of 2 linear equations with 2 unknowns, represented by the constants A and B. Professor Paar then provides a concise, yet elegant, solution for these equations, yielding the following expressions for the unknown constants. A equals S2, S3, asterisk inverse, S1, S2, mod M, and B equals S2, S1, S2, asterisk inverse, S1, S2, asterisk S3 mod M. This elegant solution underscores the fundamental flaw of LCGs, their predictable nature. Professor Paar concludes by forcefully emphasizing the cryptographic inadequacy of LCGs. Due to their susceptibility to cryptanalysis, LCGs are deemed unfit for deployment in secure cryptographic applications.